Hey guys, sorry about that. I decided not to remake the whole video, so you'll just have to tag these two together here. Okay, so we left off with identifying that we need a position, right? We're trying to compare the fact that I know I have 500 tons at t equals 0, and so how much do I have at t equals 8, which is my other endpoint, and t equals 4.92348, which is my potential relative maximum, right? Because again, we're trying to find total maximum, or the ultimate maximum amount, okay? And so we set up our desired position formula here. My x sub a, I was given that I had 500 tons, given time, which was 0, and so desired time, I have two desired times, so I have two of these set up here. One of my desired times is going to be 8. The other desired time is going to be this 4.92348. Right? Okay, and then in here we're going to go ahead and put our derivative. Again, we are at the plant, and so this is my g of t minus 100, the amount arriving minus what's leaving, what's being processed. Okay? Again, if you need a review of how to put this into your calculator, let me know when we come back from spring break, but I'm assuming we can do this. Right? And so if you take this and you plug this into your calculator, you get that at t equals 8, we have 525.551 tons. And at t equals 4.92348, we have 635.376 tons. Right? And so where am I at my maximum? My answer, okay, would be at t equals, or what is the maximum amount? My maximum amount would be at t equals 4.92348. So this would be my maximum amount. And then your third point is for your justification. So a justification would be the work supporting your answer, right? This is different than an explanation. An explanation would be describing it, right, in words. Justification would be the work to support it, would be your third point here. So reminder with number lines, you would need to do more than just draw the number line. You can't say just look at the number line. They do expect some sort of explanation corresponding to a number line because the number line doesn't count as justification on the AP test. Okay, so just a reminder, if you did choose to do a number line instead of plugging values in, you wouldn't be able to count your number line as justification point. Okay? Okay, number 2 then. Number 2, we have a particle moves along a straight line for 0 to 5. The velocity of the particle is given by -2 plus the quantity of t squared plus 3t all to the 6/5 minus t cubed. Okay, so my first step is going to be to say, okay, let's go ahead and take that function there and plug this into my calculator. Okay, so we're going to go ahead and go to y equals. And let's plug in -2 plus the quantity of t squared, which I'm going to call x because I'm going to put it into my graphing calculator, into my y equals, plus 3x to the 6/5 minus x cubed. Right? Okay, and this is between 0 to 5, so I'm going to notice I have an integral here, or an interval here, so I'm going to go ahead and constrain my window 0 to 5. Probably not going to need to go all the way up to 150, so I'm going to go ahead and start with, you know, I like always starting with 10. Again, reminder, if you don't like the guess and check method, you could take, for example, 0 and plug it in, 5 and plug it in, and determine what those values would actually be. Right? But I usually start with the guess and check. Right? So, okay, definitely started low enough and seems to have gone high enough, right? Oh. Well, maybe need to go a little bit lower. I don't know. Personally, when I'm this close to the end, I usually wait and say, okay, well, if I need to go lower, I'll change it later. All right, but I've got my graph there. Okay? And the position of the particle is given by s of t. It is known that at t equals 0, my position is 10. So I've got here, right, I'm already thinking, okay, x sub a and a potentially, if I need to use this formula, the x sub a plus the integral from a to b for some reason. Oops, I think sure this is on the screen there. Okay, and so A says, find all values of t in the interval 2 to 4, so now I've got a different interval, for which the speed of the particle is 2. Okay, this one here was worth 2 points. The first point was for considering that speed has to equal 2. Well, speed, remember, speed is the absolute value of velocity. And so your first point is for saying, okay, A, the absolute value of velocity, speed, is 2. Okay? Second point is for the answer, right? So there's a couple of different ways you could do this. You could calc an intersection here. You could subtract this 2 over and calc a 0, right? I would probably not recommend solving it by hand. I would definitely recommend, because it's still a calculator problem, right? First year calculators would definitely recommend one of those two. And so I'm going to go ahead and choose the subtraction part, right? Personally, I always like solving for zeros. Right? And so I'm going to go to my graphing calculator. I'm going to go to my y equals here. Okay? And rather than erase this, because I'm still thinking, well, I don't know whether or not I'm going to want to use this velocity. I definitely don't want to type it in all again. And so I'm just going to uncheck it. I'm going to hit F4. Again, on the 84s, that would simply look like going to your y equals and highlighting over the equal sign. If you could click enter, and now there's a highlight there, now your graphic calculator is using that function. If you hit enter and it's not highlighted, then your graphic calculator is not using that function. Okay? Okay, so I've unchecked it, so let's go ahead and type in. We have absolute value, my -2 plus x squared plus 3x to the 6/5 minus my t cubed or x cubed. And then this is -2. And I notice I've closed off my absolute value before I've hit my -2. Okay? Maybe do a quick little double check that it matches your formula here. Looks good. Okay, and so then you're going to go ahead and graph it. I can see here that I equal 0 here, here, and here. Okay, but I do have a constrained interval here, right? I only want the points between 2 and 4. So as I'm calculating my zeros, I know I'm not going to use this one over here, right? This is way less than 2, right? It looks like it might even be 1 exactly, but I don't really care what it is, right? And so then we're going to calc our zeros. I'm primarily concerned with these two zeros, because that looks like those two would be between my interval of 2 to 4. Right, so we have our lower and our upper. 84s might ask for a guess. They'll calculate, okay, 3.12763. So there's one of them. And then your other one, your 0, lower, upper. 84s would ask for a guess potentially. And you get 3.4734. Right, and if you got those two zeros, you'd get a second point for your answer. Okay, so speed is 2. Calc the zeros. Or again, you could calculate your intersections. It is a calculator problem. This is 2 points here. Okay, B. B says, write an expression involving an integral that gives position s of t. And you're like, oh, okay, well, there we go. I was already kind of prepared for that. Write an expression involving an integral. And then use this expression to find the position at time t equals 5. This was 2 points. First point is for that position formula, or position expression. Okay, so we have our x sub a, my given position, which was 10, plus my integral from a, my given time, which was 0, to my desired time, which I'm going to go ahead and call my desired time, actually, you know what, let's call this s sub x here. Right? Oh, nope, they wanted us to call it t. So we're going to call it t. My apologies. Okay, we're going to go ahead and call it t. And so my desired time up here would be t, which means my velocity, I would want to call that like x or something like that, right? Just so that we had two different variables. So we would want to call them t's because they said write an expression that gives s of t. Okay? And so this one would be a point here. And then your second point would come from using that to actually find 5. So you're going to go from 0 to 5 of your velocity. And then again, it's a calculator problem, so you'd take that, you'd use your calculator, you'd let your calculator do the work for you, and you'd get negative 9.207, right? And so this would be a point for that answer. Right, pretty much direct from Unit 7. Again, showed up on your quest. So, okay, C. C says, find all times in the interval 0 to 5 at which the particle changes direction. Justify your answer, right? Okay, so you're thinking, how does a particle change direction? Well, particle changes direction if my velocity equals 0 and changes from negative to positive or positive to negative, right? Indicating that we've changed from going right to left or left to right. And then justify your answer. This one here was worth 3 points. And your first point is essentially for defining where a particle changes direction. Your first point is considering that the velocity equals 0, right? So maybe it's not defining the whole thing, but it's for this first step. If you had written velocity equals 0, you got a point. Okay? The next 2 points are for your answers with justification, because there are 2 spots on 0 to 5 where my particle changes direction. Right, so I'm going to come back to my graphing calculator here, and I'm going to now uncheck my speed function, because I don't want speed to be checked anymore, and I'm going to recheck my velocity function. I'm going to graph it again, and I can see that here's one spot where my particle has changed direction because my velocity equals 0, and I've changed from negative to positive. Here's another, as I change from positive to negative. And if you calc those 2 zeros, right, you get that the first one is at 0.536, and then your second 0 is at 3.317, right? And then again, you would need to have some sort of justification for it. Justify your answer. Since you haven't really done any work, that's where you would then describe this whole negative to positive, positive to negative interaction. Okay? This here is how I wrote it. And you can see the points, the 3 points you'd be getting for C. Okay? Velocity equals 0, which was the first point we already talked about. And then T equals 0.536 and 3.317, because at t equals 0.536, velocity changes from negative, meaning the particle is moving left, to positive, the particle moving right. And at t equals 3.317, velocity changes from positive, the particle moving right, to negative, the particle moving left. Right? Okay, D. D reads, is the speed of the particle increasing or decreasing at time t equals 4? Give a reason for your answer. This one was worth 2 points for the conclusion with reason. Okay, so a reminder, for speed to increase or decrease, this requires us to look at both velocity, and we're looking at 4, so velocity at 4 and acceleration at 4. If they have the same sign, then that means speed's increasing, because both velocity and acceleration are positive, or both velocity and acceleration are negative. If they have opposite signs, then that means speed's going to be decreasing, right? Because they're fighting each other. They're in opposition to each other. One's positive, one's negative, right? So, as I'm looking at t equals 4, I have my handy little graph here. I can see if I trace here, F3, and I type in 4, I can see that at t equals 4, my point is negative 11.4758. Right, and I noticed that that's off the screen. If you wanted to see it, right, you could make this a little bit lower here. Again, you didn't technically need to see it. We could tell that our velocity was at negative 11, but again, if you were wanting to see your little cursor, you would simply regraph it. So you could see it here. Okay, so now you can see your cursor here. My velocity at 4. My velocity at 4 was that negative 11.4758. And then if you're like, okay, so I got my velocity is negative, I need to see what acceleration is. Well, acceleration, remember, is the derivative of velocity. You could take this derivative by hand, but again, it's a calculator problem. Your calculator can do that derivative. Second cal, or F5. Derivative's down here, number 6. dy dx, and you can say, okay, what's my derivative calculator at 4? And you type in 4. Hit enter, you'll say your derivative is negative 22.295. My acceleration is negative 22.295. And so because they have the same sign, both are negative, my speed is increasing. This was how I wrote it. Speed is increasing at t equals 4 because a of 4 and v of 4, which I've defined down here, right, have the same sign. Both are negative. This would be 2 points for your conclusion with reason. A reminder, if you're going to call something a of, if you're going to say a of 4, make sure you've defined a of 4 somewhere, right? You can't just pull that out of thin air. Okay, number 3. Last one here. Number 3, we are given that hot water is dripping through a coffee maker, filling a large cup of coffee. The amount of coffee in the cup at time t between 0 and 6, I'm like, okay, I've got an interval, important to know. It's given by the differentiable function c, where t is measured in minutes, so I'm, okay, minutes for time. C of t is measured in ounces, right? So I've got ounces. If I'm looking at a velocity or a derivative, I'm thinking ounces per minute. If I'm looking at acceleration or a second derivative, I'm thinking ounces per minute squared, right? C, reminder, right? This is the amount of coffee in the cup. Let's go ahead and write that. Amount of coffee in cup. Right, so all that's just, again, stuff we've just kind of pulled from the problem. Here's my table. Okay, I'm already thinking table. I'm already expecting a right hand or a left hand or a midpoint or a trapezoidal Riemann sum, right, with tables. Something to just kind of be ready for. Right? Okay, so part A. Use the data in the table to approximate C prime of 3.5. Show the computations that lead to your answer and indicate units of measure. This one here, ladies and gentlemen, let me pull my rubric up, was worth 2 points. 1 was for the approximation of C prime of 3.5. And 1 was for the units. And so you might start there. Right? Because we already recognized that our units were ounces for C, minutes for T. This is C prime. This is a derivative. This is a velocity of my C, which was in ounces. And so velocity with ounces would be ounces per minute, right? So you might just write this on your paper, ounces per minute. And that's a point for the unit. Okay, for the approximation, we're approximating at 3.5. Well, 3.5 is located right here, right, between 3 and 4. Okay, if I had an actual function for C, I could actually take its derivative and plug in 3.5. Make note, by the way, that this is a non-calculator. Right? So you could actually take the derivative. In this particular case, we don't have a function, so now we need to do something else to figure out what our derivative is. So you're going, okay, what's a derivative again? Oh yeah, derivative is slope. Well, I know how to find slope. I found slope since like pre-algebra days. Slope is change in y, so my 11.2 and my 12.8, minus, or over, sorry, over change in x, my 3 minus my 4. Change in y over change in x. It's like, okay, I can approximate 3.5, the in-between of these two numbers, by doing slope. Change in y over change in x. That's what a derivative is. Derivative is slope. And so you'd have your, I'm going to write 12.8 minus 11.2, subtracting over 4 minus 3. And that would be a point with your ounces per minute, which would be the second point. Again, you wouldn't have to simplify all the way. If you did, you'd get 1.6 ounces per minute, which would again be 1, 2 in terms of points. 1.2 points. Okay. B, we are asked, is there a time t between 2 and 4 at which C prime of t has to equal 2? And justify your answer. Okay, So, okay, so between t and 4 is there a place where my c prime of t has to equal to. Okay, there's two different ways to approach this problem. Okay, we're going to walk through one, and then I'm going to show you another route that I went, right? This particular one was worth 2 points. Okay, our first point was for c of 4 minus c of 2 over 4 minus 2. The second point was for your conclusion using mean value theorem. Because the first route that we're going to talk through here is to justify a particular derivative, to say yes, that derivative exists, we can use mean value theorem, which says that your f prime of c, your derivative, equals f of b minus f of a all over b minus a. Now, it does have to be, therefore, differentiable and continuous, but we're told that c is differentiable, right? Remember that phrase I said you want it in your back pocket anytime you're guaranteeing something. Differentiable function. Right? Okay, so if we want to guarantee that c prime of t equals 2, the question is, can I find an f of b minus an f of a over a b minus a that equals 2? Well, the easiest a and b that I see to use, to start with at least, would be 4 and 2. They told us to use them, right? F of 4, let's call it c, c of 4 minus c of 2 all over 4 minus 2. Well, c of 4 here was 12.8. C of 2 was 8.8 over 4 minus 2. 12.8 minus 8.8 is 4. 4 minus 2 is 2. And 4 divided by 2 is 2. So if you had gone this route, this would have been a point right here for considering the c of 4 minus c of 2 over 4 minus 2. Okay, the second point would have been for your conclusion using mean value theorem. And so this is how they wrote it when they solved it. Or on their rubric, I should say, right? C is differentiable and C is continuous, right? C is a differentiable function. Keep that phrase in the back pocket. C of 4 minus C of 2 equals 2. That's what we just did on our paper. Therefore, by the mean value theorem, there is at least one time t between 2 and 4 for which C prime of t equals 2. And you can see your 2 points here. Okay, the other route that my brain took when I did this was using approximations, identifying that 3.5, which we had identified earlier, our derivative at 3.5. Remember this in part A was 1.6. So I approximated my derivative at 2.5 as well, using the same technique. It would have been 8.8 minus 11.2 over 2 minus 3. And when I approximated that one, I got 2.4. And so then I used IVT when I was solving this one, right? 2.4, 2's between 2.4 and 1.6, which are the approximations of C prime. And since C is a differentiable function, therefore there must be a spot between 2 and 4 where C prime equals 2, IVT, like what we used on the train one in 2014A, or 2014B, sorry. Okay, C. C says, use a midpoint sum with 3 subintervals of equal length indicated by the table to approximate the value of 1/6 the integral from 0 to 6 of C of t dt. Using correct units, explain the meaning of 1/6 integral from 0 to 6 of C of t dt in the context of the problem. This was worth 3 points. Excuse me, sorry. The first point was for using a midpoint sum with 3 subintervals. Right? If you had done the midpoint sum with 3 subintervals, you would have gotten a point. And in this particular case, we are approximating 0 to 6. Right? So as I look at my table up here, 0 to 6, 3 subintervals. So to get from 0 to 6, I would be counting by 2's to make 3 subintervals, right? So 1, 2, 3. So I can see my 3 subintervals here. 3 subintervals. So midpoint, first subinterval, we have our change, which is 2, times our midpoint, which would be 5.3. And I'm going to change these to parentheses so the decimals of multiplication don't start to look the same. Second subinterval, we have our change, which is 2, times our midpoint, which is 11.2. Our change, which is 2, times our midpoint, which is 13.8. And that right there is a point. The second point is for the actual approximation, right? Because we are looking here to approximate the value of 1/6 of that integral, right? And so if you had taken this addition value and you had either gone all over 6, or you had put parentheses around it with a 1/6 out front, if you leave it there, that's a second point for that 1/6 of that integral. Okay? If you did choose to simplify all the way, in this particular case, you would get 10.1 ounces. Right? But again, non-calculator and you're timed and it's a free response, you don't have to simplify. I wouldn't. The third point is for the interpretation, right? So you're asking yourself, okay, what does this mean? And make note, you do have to use correct units. Okay, so 1/6 integral from 0 to 6 of my c. What does that look like? What equation does that look like that I've been using? And so I'm thinking, okay, integrals with a fraction out front. When have I done that? Well, we do that all the time with average. Go ahead and turn my page here, right? My average is 1 over b minus a times the integral from a to b. So if my a was 0 and my b was 6, my b minus a, 6 minus 0 would be 6. Oh, that's the average formula. Okay, so I know how to explain the meaning, right? Using correct units, this is the average from t equals 0 minutes to t equals 6 minutes. Amount of coffee, because that's what c was, right? C was the amount of coffee. It's the amount of coffee in the cup, right? This is how I wrote it when I did it. 1/6, the integral from 0 to 6 of c of t, is the average amount of coffee in ounces that is in the cup from t equals 0 minutes to t equals 6 minutes. Okay, and then last one here, D. D, we are told that the amount of coffee in the cup is modeled by this function. Using this model, find the rate, so find the derivative at which the amount of coffee in the cup is changing when t equals 5. This final part here was worth 2 points for doing that. Right? Your first point was for, okay, what's the derivative? Because we need to find the derivative at 5. So to find the derivative at 5, I first need to know the derivative. Okay, so my derivative 16 is 0, negative 16 is a coefficient, and e to the u is e to the u times u prime, 0.4. And that would have been a point for taking the derivative. And you wouldn't have had, you could have not had the 0 out front here or done, the 2 negatives makes a positive. Like you can simplify this sum if you want, but you don't have to. And then your second point would have been finding that derivative at 5. 0 minus 16 e to the negative 0.4 times 5 times negative 0.4. And that would have been your second point. And again, you could simplify it. If you simplified it, you'd get 6.4 over e squared. But why take the time to simplify it? It's a waste of time when you could now be moving to another problem or adding to your explanations or that type of thing. Yeah. There you go. I hope you have a fantastic spring break. I'll see you when we come back.